it certainly makes sense to wonder why one has to define a multiplication between two matrices with such a complicated formula as we've seen in the previous lecture. So why not, for example, define a multiplication of two matrices of the same dimensions component-wise, just like we did with the sum? Well, the reason for this is it will be evident in a theorem that we will cover in few lectures when we will introduce linear maps between vector spaces. So at this point, just take this formula as some made up definition with no real purpose at this point. But of course, that is the only definition that will enable to prove the theorem, that will be extremely helpful regarding linear maps. And let's analyze and list a few of the properties that this product structure has on certain vector spaces of matrices. So, properties. So one may wonder if there exists a matrix vector space MHK on which the product, as we defined before, is an inner structure, meaning that if I take any two matrices inside, I can actually define a product of these two matrices inside that set. Well, the answer is the following. The product is an inner structure of MHK if and only if H equals to K. Okay? So if H equals to K, these matrices are square matrices. They have as many rows as columns, and they all have the same number of rows and columns. Therefore, taking any two matrices inside that set, the product is well defined and will still be an MHH matrix. Okay, so this is an important fact. When we will talk about product structures in a set of matrices, we will have to restrict ourselves to spaces, vector spaces of the kind MHH. Now, since the product is an inner structure in MHH, one may wonder the next step. So, is it a group structure on MHH? So remember, when we introduced vector space structures, we said that the vector space must have an additive structure, so an plus operation inside the set, and this operation has to satisfy a number of properties. The first one was associativity. Okay, so associativity in terms of products is stated as follows: A times B, so this product times C, is this equal to A multiplied by the product of B times C? The answer is, in this case, yes. Okay, the product is associative, so this property holds. So we may continue and see the next one, if holds, and see if you are lucky that these will be a group with respect of the multiplication. So next property was the existence of an identity element. Existence of an identity element 1 okay, which means a matrix let's call it ID H, because it has to belong to this vector space MHH, therefore it has to be square with the dimension H, matrix A identity H, such that identity H times A equals A times identity H equals to A for every A in MHH. Okay, and the answer to this is yes again. Why is that yes again? Because I will present you what is this matrix. So this matrix is the following. So if we take as identity H the matrix, the square matrix that has ones along the diagonal, all the diagonal elements are 1, and on the top all the elements above the diagonal will be zeros, and all the elements below the diagonal will be 0. Okay, so this matrix is immediately verified to be an identity matrix for this product structure. You can easily verify it using the definition of product. So we are almost convinced that it is a group with respect of multiplication, but we still have to verify the last property. The last property is the following: is existence of inverses. So what is an inverse? Given A in MHH, does there exist a B in MHH such that A times B equals B times A, which in turn equals to the identity matrix? And the answer to this is no. Okay, so this is the only property which fails among those necessary to make MHH a group with respect of the multiplication. Well, let me give a counterexample. So a matrix which has no inverse, no inverses. Well, if the inverse exists, is unique, so no inverse. For example, we already have examples for h equals to 2. Well, for h equals to 1, M11 is simply the set of real numbers. These are matrices in which there is just one coefficient. Okay, so the set is the same as real numbers, so we know that real numbers are a field. Therefore, the multiplication of matrices is a generalization of multiplication inside a field. So if we restrict this definition in the case the vector spaces of matrices are just M11, then we will see that this multiplication of matrices is exactly the same as field multiplication inside R, the real numbers. Therefore, we have the first non-trivial case, which is for h equals to 2. So example, in M22, consider the matrix A equals to, I don't know, 1, 2, 2, 4. Okay. So this matrix has no inverse. Has no inverse. Now, how do we prove that? So either you just take any other 2 by 2 matrix and you leave the coefficients unknown, and then you use the 4 conditions you get from the multiplication here rule. So basically you get 4 equations in these 4 variables, and you have to solve this system of linear equations. In a sense, we will talk about this later, and you will see that this system has no solution, or else you just have to trust me. We will do some we will cover some very quite deep theorem in a few lectures, which will allow us to immediately see why this matrix has no inverses, saying that this product structure does not give a group structure to MHH does not mean that there are no matrices with inverses. Okay, so lack of all inverses does not mean that some matrix will have inverse. Okay, for example, so this has no inverse. On the other hand, A equals 2, 1, 2, 1, 4. Well, this one certainly has inverse. Has an inverse, which we will say it is invertible. And its inverse we will denote as A minus 1. Okay, I cannot tell you. Of course, I can compute what the inverse is, but the point here is not showing you that this has an inverse, but just to tell you that I'm using a theorem right now, which I cannot state, which will imply automatically that this matrix is invertible without me having found its inverse. This is some power of mathematics. Sometimes theorems tell you some properties of some objects without actually constructing the objects that give them this property. For example, here the property is invertibility of A, and of course I can prove invertibility of A showing you its inverse. However, I'm using now a theorem that we will cover in few lectures, which tells me that this A is invertible without actually giving me an inverse of A. I know that it exists, but I don't know what it is. There is an extra property, or at least lack of, which I would like to talk about, which is commutativity. Commutativity. Okay, so remember that commutativity amounts to the following property: if A times B equals to B times A. Okay, so in general, if we are not restricting ourselves to MHH, A times B might exist, but B times A might not even exist. Now, if we restrict ourselves to MHH, as we said before, both of these matrices exist, H times B and B times A. So it is legitimate to ask whether these two matrices are equal, and in general, this is not the case. So this property fails as well.